Now, this is the last type of proof by induction. So this one is on inequalities. Now, one thing before we start an example, two things that you may find useful along the way for some of the proofs. Part one, if A is greater than B, then A minus B is greater than 0. And then for the second one, any real number is squared, so that includes any negative number. Any negative number squared is a positive number, and any just normal number is always a positive number as well. So the first example we're going to look at here is the proof by induction that 2 to the power of n is greater than n squared for n greater than or equal to 5 for n an element of n. Now the one thing that is slightly different in this one compared to the other two types, for the series of numbers and for the divisibility, you always start at n equal to 1, but for this one here, the inequality ones, they will tell you what to start at. So this one here is telling you to start at 5. So when we're writing out our steps, I have the steps written out again. All I've missing is the blanks in the middle for the first three parts. But when we're writing them out, this time you're going to be talking about n equal to 5 as your starting point. So prove the statement is true for n equal to 5. So you're not going to start at 1 because it won't work. Assume true for n equal to k, where k is greater than or equal to 5. Again, the wording of the next one is going to be the exact same as the previous two types as well. It's based on the assumption we must now show that this statement is true for n equal to k plus 1. And then you carry out the actual proof itself. Then at the end it is, but since it is true for n equal to 5, it must be true for n equal to 5 plus 1, which is equal to 6. And then if it's true for n equal to 6, it is true for n equal to 6 plus 1, which is 7, etc. And then from that, therefore, it is true for all values of n greater than or equal to 5 for n an element of n. Okay, so like I said again, the steps itself, we've got most of the steps there done already. The big part now we have is to fill in the values for the first and the second part, and then the third part we have the proof to do. But like I said, if we can do the first two parts and the last two parts, we've got 4 out of the 5 steps done, which will give us quite a lot of marks in the exam already anyway. Okay, so looking at the very first one, we have to prove the statement is true for n equal to 5. So putting in n equal to 5, we have 2 to the power of 5 is greater than 5 squared. So we're going to try to prove that this is true. 2 to the power of 5 is 32. 5 squared is 25. 32 is greater than 25. Therefore, true. And you can write true for n equal to 5 or whatever you like there. So these 3 dots just stand for true. Therefore, true. Okay, so the next one we have to do is assume true for n equal to k, where k is greater than or equal to 5. So we're going to, everywhere we see k, or everywhere we see n, we're going to change it to k. So it's going to be 2 to the power of k is greater than k squared. K is an element of n, and k is greater than or equal to 5. Okay, so they're just the two things that we're stating there. This really and truly is what we're looking for. Everywhere you see n, you're changing it to k. So we have the first 2 steps done. Then we're on to the actual proof of the thing itself now. So we're going to keep this assumption just up here so we can see it, because this is our assumption that we're going to use. And we're going to write down what exactly do we have to prove. So we're trying to show, is 2 to the power of k plus 1, is that greater than k plus 1 squared? Now, since 2 to the power of k is greater than k squared, we're assuming this already. So this is the thing that's assumed. Therefore, we know that 2 to the power of k by 2 is greater than 2k squared, because you're just multiplying by 2. And then therefore, we also know that 2 to the power of k plus 1, which this essentially is greater than 2k squared. So then this is what we're going to try to work with next. Now, it was very difficult for us at the very start to be able to try to prove that this is greater than this part here. But what we've done is we have rearranged now the 2 to the power of k plus 1, which we have here. We've said that that is greater than 2k squared. So if that is greater than 2k squared, now what we have to try to prove is that 2k squared is greater than k plus 1 squared. And that's going to be much easier for us to do. What we can do in our first step is if we multiply out the right-hand side, the left-hand side stays the same as it is. So we've got k squared plus 2k plus 1. So you square the first, square the last, first by last by 2. It's a quick way to square it out. We take everything to the same side. So it's going to be k squared minus 2k squared minus 1 is greater than 0. And then what we have is we're going to try to complete the square here. So it's going to be k squared minus 2k squared. We're going to, sorry, it's minus 2k. Apologies. So we're going to plus 1, and then we're going to minus 1, and then we already have our minus 1 that's already there, and that is greater than 0. So we're trying to complete the square. We'll just get that completed now in a second. So completing the square of the bit in the middle, it's going to be k minus 1 squared, and then minus 2 is greater than 0. Then we're going to take that all up here. So for k minus 1 squared minus 2 is greater than 0, we know that is going to be true for k greater than or equal to 5, since we have that up above. Okay, and then we have, therefore, 2k plus 1 is greater than 2k squared, and then that in turn is greater than k plus 1 squared. So then, therefore, it is true for n equal to k plus 1. And then since it's true for n equal to k plus 1, we know that it's true for n equal to 5. It must be true for n equal to 5 plus 1, which is 6. And if it's true for n equal to 6, then it is true for n equal to 6 plus 1, which is 7, etc. And then therefore, it is true for all values of n greater than or equal to 5 for n element of n. For that example, step 1, 2, 4, and 5 again are very normal. They're very doable. The very difficult part for that one is figuring out what you have to do to work out this part in the middle. That's why try to do as much as you can at the start of it, and if you're unable to get this working out part, write your conclusion over here. It is true for n equal to k plus 1, and then continue on with the two bottom steps as well. I wouldn't worry too much itself about the actual proof in the middle. As long as you've got the steps, you get the majority of the marks for the question.